In this part, we'll look at multi-arm bandits. Multi-arm bandits aren't solutions to MDPs themselves, but they are a key component of many different reinforcement learning solutions, so we're going to take some time to discuss them. We'll frame what a multi-arm bandit problem is, we'll look at some of the solutions to multi-arm bandit problems, and we'll compare and contrast the strengths and weaknesses of different multi-arm bandit algorithms. For multi-arm bandits, there are two primary learning outcomes. At the end of this part, we expect you to be able to select and apply multi-arm bandit algorithms for a given problem, and to compare and contrast the strengths and weaknesses of different multi-arm bandit algorithms. Let's get started. So let's just start off with an intuitive idea of what a multi-arm bandit is. A multi-arm bandit, also known as an n-armed bandit, can be illustrated as follows. This is a so-called one-arm bandit, which is named due to the arm on the side. This is otherwise known as a slot machine or a poker machine, as they're called here in Australia. You can pull the arm on this, or the lever, and you can win a prize, and the probability that you win a prize is governed by some underlying probability distribution that we don't know, and we can play as many times as we want. So a multi-arm bandit problem is as follows. Imagine that you're giving n number of these. In this case, we've got 3. Each of these machines has a different probability of winning, and we don't know what the probability is beforehand. The question is, can we select a number of strategies where we pull different arms at different times in order to maximize the amount of times we win over, say, an extended period or over an infinite amount of time? If so, how should we select those? Multi-arm bandit techniques aim to solve this problem. Now let's look at a more formal definition of a multi-arm bandit problem. Remember, there are n different arms, and we get to select a different arm in a series of steps. We're going to represent this problem using a series of random variables. The random variables x, I, k represent the reward we get if we select arm number I in play number k. So we're going to get a series of such plays, playing arm I in round 1, then playing arm J in round 2, then playing arm K in round 3, etc. The aim is to derive a strategy that selects arms in each round in order to maximize the cumulative sum of the rewards that we receive over each of these plays. As discussed already, because we don't know the distribution of the rewards that are provided by each bandit, we need to take samples to gain information, and then we can use this information to make better choices. Taking samples is known as exploration, and using the resulting information to make better decisions is known as exploitation. But the problem is, how often should we explore and how often should we exploit? This drives us to search for strategies that minimize what we call regret. So regret is the loss that we have when we choose an option that's not the best option. Let's have a look at this a bit more formally. If we sample an arm that is not the best arm, we'll end up with some suboptimal selection. The difference between the best reward we could have received and the reward that we do receive is called our regret. Before we formally define regret, let's introduce a new concept known as a Q-value. A Q-value is a very important concept in reinforcement learning, and we're going to use a simplified version of that at the moment, and we'll extend on it later. We define the Q-value, Q of arm A, as simply the average reward we've received from playing arm A so far. This can be defined more formally as the sum, starting at I equals 1 up until round T, which is the current round, the reward we received if we played arm A in step I. If we didn't play arm A in step I so far, this X here would be 0, otherwise it will be the reward that we received. We use the syntax Q star A to represent the real Q value for A. In other words, the actual average reward we would receive if we played arm A. We don't have access to Q star A while we're trying to learn this, but it's useful for analyzing how we should solve the problem. Now let's introduce the concept of regret more formally. So let's assume we have access to this Q star function that can give us the real Q value, or the real expected reward for every arm A. We can define the regret of selecting a particular action, let's say B, as follows. We'll use the letter R to refer to this regret. And the regret is simply the difference between the Q value of the best action minus the reward we actually received. The value of the best action, subtract BK, where B is the action we did play and K is the round that we played it on. So this just gives us the regret for a single round. But we can also quantify the regret over a series of T arm pulls, number of T arm pulls, using a particular policy pi. Now remember, with a policy pi, we're going to be sampling different actions and playing different actions, so we won't play the same action every time. We'll play the action defined by our policy. So in that case, what we're going to do is we're going to substitute this B over here with the expression pi K, which is the arm we would pull on round K. And we're going to define the reward of policy pi for the first T time steps. We can do this by simply taking the maximum reward we could get over that time, which is T, and subtracting the expected reward we would receive for using our policy over that time step. We're going to use our familiar expectation reward here for summing up each round K starting from 1 up to round T. So this gives us the regret of using policy pi up to time step T. Informally, what this says is, if I use policy pi, my regret is the value of the maximum set of possible rewards we could possibly have gotten up to round T, subtracted by the expected reward we receive by playing policy pi in every round up to round T. If pi is optimal, then I always take the best action and my regret would be 0. A zero regret policy is not a policy whose regret is actually 0. It's a policy whose average regret each round approaches 0 as the number of rounds, the number of pulls, approaches infinity. Therefore, a zero regret policy is one that converges to an optimal policy after an infinite amount of time. The aim of a multi-arm bandit strategy, therefore, is to derive a policy, a zero regret policy, that will minimize our expected regret over time. Before we look at techniques for solving multi-arm bandit problems, let's just consider a very simple, abstract example of a multi-arm bandit problem with 5 arms. There's 5 arms named A to E. Each arm gives a reward of 5 based on some probability. So for example, action A gives a reward of 5 with probability 0.1 and a reward of 0 with probability 0.9. Action B gives a reward of 5 with probability 0.3. Action C, 0.7. Action D, 0.2, and action E, 0.1. So each of the bandits gives the same reward, 5, but with a different probability. Therefore, arm 3 will provide the highest reward if we select it every time. But remember, we don't know this initially. So we have to figure out which arm is the best for us. We're going to use this very simple problem to experiment with several different multi-arm bandit techniques. In these experiments, an episode of the problem has 1,000 plays of each arm, or 1,000 arm pulls. We're going to run 2,000 different episodes so that we get a bit of stability in our data. Epsilon greedy is a simple and effective algorithm for balancing exploration and exploitation. In epsilon greedy, we have a parameter, epsilon, which is somewhere in the range 0 to 1. Using this parameter, epsilon greedy works as follows. With probability 1 minus epsilon, we choose the following. That is, we choose the arm with the highest Q value so far, or the highest cumulative average reward so far. And with probability epsilon, we choose a random action. Choosing random with probability epsilon is the exploration part, while choosing argmax with probability 1 minus epsilon is the exploitation. Well, on the top right here is a graph that plots the average reward over 2,000 episodes and 100 steps each, using the simulator that we talked about earlier. We can see that smaller values of epsilon, such as 0.05 and 0.1, do quite well in this problem. As they approach 1,000 steps, 0.05, which is in some sense the most greedy solution, starts to receive a higher reward than all of the other ones because it's not choosing random actions as much. Things such as epsilon at 0.8 choose random actions far too often to learn anything useful. So in this case here, you can see at around about probably step 40 or 50, the Q values are fairly well learnt by this algorithm here, but at 0.8 they're not exploiting enough. Therefore we see that reasonably low epsilon values can work well. A value of epsilon equals 1 is just the same as choosing a random action all the time. We never choose the argmax action. Epsilon greedy works quite well, but it has a weakness. What do you think it is? Well, if we look back at the graphs, we can see that after a while, epsilon greedy learns the Q values quite well, but it's still, some of the time, choosing random actions. We improve our exploitation by choosing less random actions once we have good Q values. Epsilon decreasing is a simple extension to epsilon greedy that helps to do this. As well as having the parameter epsilon, epsilon decreasing has a second parameter, alpha, which is also in the range 0 to 1. The alpha parameter is a parameter that helps us to reduce the amount of exploration that we do later on. On each play of an arm, we take our epsilon and we assign it epsilon times alpha. For a value of alpha less than 1, this means that the amount of exploration we do gets smaller after each play because epsilon becomes smaller each round. This means that we explore less and exploit more as we gain more information. A good value of alpha is dependent on the particular problem that we're using, but again we can experiment with these using our simulator. On the top right is a graph that plots the average reward for the different values of alpha using the same simulator as earlier. We can see that values close to 1, such as 0.99 or 0.999, do quite well because we don't want to reduce our exploration parameter too quickly as we do with alpha 0.9. What we want to do is reduce our exploration parameter quite gradually so that we have time to learn accurate Q values, and then after that we can exploit them. Epsilon greedy and epsilon decreasing work well, but they have a problem. What if the probabilities in our underlying multi-arm bandit problem change after a while? That is, what if the random variables change over time? This is known as non-stationarity. If epsilon becomes too small in epsilon decreasing, it'll stop exploring and the information that we have will be outdated. Softmax is a strategy that aims to overcome this. You might be familiar with the softmax function if you studied topics such as statistics or machine learning in the past. The idea behind softmax is to choose our arms based on a probability distribution that's generated from the Q values for each of those arms. In other words, the higher the Q value is of an arm, the more likely it is to be selected at each time. Formally, we use what's known as the Boltzmann distribution to model this. So let's have a look. The way we model this is to say that the probability of an action A being chosen is modeled as a Boltzmann distribution. A Boltzmann distribution says e to the power q of A divided by our denominator, the sum of B, E, Q of B. In other words, the probability of selecting action A is E to the Q of A, where Q of A is the Q value of A, divided by the sum of the E to the Q values of all of the arms in the bandit. Because this denominator down the bottom is the same by summing up all of the actions, the same for every action we choose, if we calculate this expression for every arm A, we get the probability distribution over arms. Then we choose an action randomly using that distribution. This will naturally explore different arms, but it will do so carefully to ensure that arms that appear to be really bad are not sampled very often, but they're still sampled enough such that if their Q value is inaccurate, we will learn the accurate Q value over time. Often, we add a temperature parameter in the Boltzmann distribution. For this, we simply divide by a parameter tau each of these expressions here, where this t-looking character is our tau character. The temperature parameter tau dictates how much of an influence past data has on the decision. A higher tau would mean that older data has less influence, making this more robust to change. So we can think of any value of tau greater than 1 as kind of flattening the probability distribution out. A tau of infinity would mean that actions are chosen uniformly. And as tau approaches 0, softmax would become a greedy strategy, choosing argmax Q of A for every move. The graph here looks at the effect of different values of tau on our abstract example earlier. In this case, because the problem is stationary, that means variables underneath don't change, tau of 1 gives us the best outcomes. As tau gets higher, we get poorer and poorer outcomes, because effectively as tau gets higher, we're flattening out that probability distribution. However, think about this. What if we arbitrarily changed all of the underlying probabilities in our simulator at, say, step 500 to new probabilities, making the old data effectively useless? Let's see what that looks like. In this graph here, at step 500, we change all of these probabilities, and we can see, of course, as expected, the performance of all the algorithms does quite poorly. The Q values we had before are now meaningless, and it's still exploiting them quite a bit in all of these strategies. However, what we see here is that tau at 2.0 recovers the quickest, and the higher the value of the tau, the more we recover, because the more we're likely to sample actions that were previously bad but are now good, and therefore learn more accurate Q values more quickly. After a sort of what looks like a few hundred steps here, all of them converge back to a reasonable strategy, and they all catch up with tau equals 1. However, even tau equals 1 does quite well, because our softmax strategy keeps exploring and eventually learns that the actions that are now good but were previously bad are good, and learns these better options again. The final strategy we're going to look at is the highly effective upper confidence bound strategy, otherwise known as UCB1. Using UCB1, we select actions according to the following formula. In this expression, T is the number of rounds that we've played so far, and NA is the number of times that A has been selected so far. So how does this work, this upper confidence bounds? Well, it says to select the action that maximizes this expression inside the brackets here. The left side of this expression, Q of A, encourages exploitation. The right side encourages exploration. Why does this strategy work? Well, I'll just give a bit of intuition, and you can explore more of it in the notes or in the further reading. We know that Q of A selects high value actions, which is good, therefore we're exploiting. But we see on the right hand side, N of A is the denominator here, which is the number of times that A has been chosen. If N of A is low relative to T, then this encourages exploration. This is more likely to be selecting action A. On the other hand, if this is very high compared to T, then it's less likely that an action can be considered. as you might realize, n will be 0 at the start for every arm. And so usually to avoid dividing by 0, the strategy that we employ is to select each arm once at the start. You can have a look at the notes to see some of further intuition about why this is a good formula. Because there's no parameters to UCB, let's use this time to compare UCB to the other strategies that we've seen so far. For epsilon greedy, epsilon decreasing and softmax, we use the parameters that did the best in the earlier simulations here. We can see that UCB performs best relative to all others. It learns very quickly what good actions are, and it converges to its optimal value much more quickly than all the others. We can see that softmax does reasonably poorly on this with tau equals 1. But what about for non-stationary problems? Let's have a look what happens when we again arbitrarily change our values in the underlying probability distribution at step 500. We can see here that, as we expect, the strategies all do quite poorly for a while. Epsilon decreasing never recovers at all. This is because by this point, epsilon decreasing has effectively stopped exploring and is just exploiting, but it's exploiting old data, and therefore this isn't going to work very well. We can see that epsilon greedy starts to improve a bit, but not so well. However, we can see that softmax recovers the most quickly, even quicker than UCB, but after a while UCB recovers reasonably well and then goes off to perform a lot better than softmax. However, softmax does recover more quickly, and remember this is for softmax where tau is equal to 1. Therefore this is the worst at recovering from all the softmax values we could have. From this we can take it that UCB1 is a robust strategy that performs very well, but in a non-stationary environment where the underlying probabilities are going to change either suddenly or quite a lot over time, UCB might not perform as well as softmax. However, in a stationary environment, UCB might perform better than all three. In this part, we discussed multi-arm bandit problems. We first defined what a multi-arm bandit problem was, and then we discussed the problem of exploration versus exploitation. We looked at 4 techniques for solving multi-arm bandit problems: epsilon greedy, epsilon decreasing, softmax, and upper confidence bounds, known as UCB1. We saw that UCB1 performed better and more robustly than the other techniques in our simple simulated environment, but it's less suitable than softmax for highly non-stationary environments. Multi-arm bandit solutions are used in many reinforcement learning techniques for solving MDPs, and in the next part of the subjects we're going to use multi-arm bandits as part of larger solutions for solving MDPs, so stay tuned.